Hello, thank you. I'm Dean Sander from IBM, and I do most of the firmware architecture for booting up the P8 processors. And what I'm going to be talking about today is the hooks that the team has put into the P8 processor that we plan to take advantage of to create the core root of trust for secure and trusted boot. So first of all, a few principles on what we want to do. So one of the guiding principles we have is that all the code in the flash is by definition validated prior to execution. So we never execute directly from flash. We always bring it into secure memory, validate it, and then execute it. So that kind of bases our design point. The design is also built around various layers of trust. Each boot starts from a clean state. So everything is wiped when you go through a boot cycle, and then we establish the core root of trust. So that involves the self-boot engine, and I've got some follow-on charts that explain that in more detail, and I'll walk through each individual step. And then the host boot base image, which is the first thing that gets loaded into the P8 processor's memory. After that, the lower layers verify the subsequent layers. So as you can kind of see, we build up that chain of trust as we continue to boot the processor up. The very lowest layer of the core root of trust resides in what we call the processor PROM, a CPROM, which has the self-boot engine, the SBE's code, that resides in it. Now, this code is updatable only by a verified host boot. So we kind of only can update the CPROM by something that's already been passed through the chain of trust. So you may ask, how do we, when we or one of the key points that we've been asked many times is do you have to have the IBM keys to boot the actual processor? And no, what we want to do is we want to have a very private public key, what we're calling the imprint key, that all of the processors will ship with, that you can then customize and replace with your own set of keys. So all the code from the host code up is open source, so you can download that, you can compile it, you can look at it, you can touch it, you can check it out, see if there's any bugs, security holes, and you can then sign it with your own key that you can pass up from your manufacturing standpoint, or if you want to allow your customers to be able to sign with their own key. So what I'm going to do now is I'm going to walk through the basic flow of how we plan to use the hooks in the processor to establish the chain of trust. So a couple of points on the actual chart. The red things, and this P NOR right here is the processor NOR. That's the flash that we use to boot off of. The red things are all the untrusted stuff. So when it's red, it's not trusted. If you look at the green areas, those are the things that are we call trusted entities in the system. So from a hardware standpoint, the things that are in green are trusted. And if you notice, the PROM right here is actually inside the P8 module. So by definition, you can't walk up to it and program it. You actually have to pull the socket off of the system in order to update that PROM. So when you start the boot on a P8 chip, the first thing that executes is this SBE code right here. It fetches the instructions from the PROM out there, and then what it does is it does the basic initialization of the hardware. Goes through and does the basic chip initialization, gets the core to the point where the core is ready to execute instructions. It also resets the TPM right down there. And then the other key thing that it does is it takes the key, which resides in this CPROM right there, which can be updated by a validated host, and moves it into what we call the PIBMEM, Pervasive Interface Bus Memory. It's just a little storage space inside the chip that can be used as temporary storage. We do that to make it accessible to the next step later on when we actually are going to use this ROM secure validation code. So after that is done, the SBE will then reach out into P NOR. It'll pull in the host boot base image, and it'll move the untrusted host boot base image into the L3 cache. Now at this point in time, the processor hasn't even executed or started instructions on that cache. It's just sitting out there. After that, the SBE will then issue the command to start the core. The core will, part of the hardware design in P8 is that when you issue the start instructions on a core, it will then automatically jump to the ROM. So even if the next instruction pointer is pointing in somewhere in memory, the first time you start it, it goes immediately to the ROM code, which is a built-in security hash algorithm. So that ROM code will actually use a couple of pieces of information from the SBE that's been placed into some of the registers in the core to find the host boot base image, find the key that it should be validated against, and verify that that image that was placed in the memory is okay per the key. If that is true, then it'll move it to, I'll call it the secure location, or a trusted location, and that changes the code from untrusted to trusted. So at this point in time, we've verified the host base image, and we're ready to start actually executing that. So after the ROM finishes its execution, it then jumps to the entry point of the base image. Then what happens is the host boot base image will load in and use the host boot extended image. So the host boot base image is just 512 kilobytes of code. There's a lot more code that's needed to validate and actually boot up the rest of the system. So the host boot base image will actually contain pages or a hash of each page that resides in the host boot extended image. So before, when we pull in a page from the host boot extended image into the cache, we will validate that that hash key matches what it's supposed to match, what's already been verified by the host boot base image. So this way we can guarantee as we page things in and out of the cache that the code we are executing is actually trusted before we go and actually do anything with it. At this point in time, the host boot code will then place the measurements of all the code that it's going to run into the TPM. So this is for attestation later on in the process. At this point in time, remember I mentioned about the ability to actually update the PROM code. So at this point in time, the host has the ability to update the CPROM code that resides in the module. This is kind of like a fail-safe if something changes in the processor initialization or if there's a bug somewhere in the processor that needs updating. It can take the SBE code image that resides in the NOR, validate that, yeah, okay, it matches the key that I currently expect, and if that passes, then it can actually write new code out into the PROM. And this is also how you can update the key if you need to update the key. So when I talk about the imprint key, since it's a well-known public-private, you can sign an SBE image that contains your own key into the PNOR and have it push it up into the CPROM, and then when you reboot, that new key will be used to verify the next version of the PNOR code. After this is done, what will happen is host boot will then lock down the PROM code. After that point, nothing in the system can update that CPROM, and you have to go through a complete full reboot to reestablish your chain of trust before that PROM code can be updated. After that, the host boot will go off and train the power bus and the memory controller and starts the other micro engines in the system, so the Sleepwinkle and the OCC. Each of those have their own code image. They will all be verified and validated before each of those is released to actually start executing. Then what happens is the same process keeps on happening. As they get validated, all the measurements get placed into the TPM. I just didn't show that. Then what we'll do is we'll load in the Opal code, we'll verify it, bring it up, and you can also have the processor open up an untrusted window if you want to do BMC or some sort of communication, but the host has control over where that window is and how big it is. So at base, this gets us up to the point where Opal's loaded. They'll then verify PettyBoot and continue on. As you can see, I don't go into any of the Linux implementation, just as to how the core root of trust is established, and then Linux takes over. So future secure boot plans. So what I just went through was a P8 version of that. For P9, we've got some changes in flight. One is that right now on P8, the SBE is just a binary image out in GitHub. For P9, we are planning on open sourcing that SBE image, so you'll actually be able to compile it and change it and modify it, and it gives more transparency from a security standpoint. We're also planning on eliminating the on-chip ROM. So for P8, the security algorithm was burned into the actual hardware. What we are planning on doing for P9 is that security algorithm will now be loaded, will be placed in the actual CPROM itself. So it's kind of got the same idea that you can place the key and the security algorithm into the CPROM and keep it secure with the same chain of trust as we did for P8. This allows for customization of security code. Once again, only the chain of trust can update the PROM. The loader and the actual algorithm then run on the host processor, kind of in the same mentality or flow. Firmware then on P9 also has better control over the unsecure window. So when are we planning on getting all of this implemented? So for P8, we are targeting a limited P8 trusted boot functionality by the end of this year. What we plan on doing is once we enable that out in GitHub, we'll start shipping the P8 modules with imprint keys. We haven't worked out all the exact details, but we are in the process of putting that code together. So if you have any ideas or questions or concerns, please let me know. Please contact me after I'm done talking. I'll be in the back. You can ask any questions that you want. I also should note that our current implementation, we're compliant with the TPM 2.0 architecture, measurement and logging. It's specific to an I2C bus. I know there's some other interest in doing the actual TPM over an LPC bus. Thank you.